I will request Professor Dinesh Bhavnani sir to please conduct the session.
Thank you, Partho sir. I request Mr. Akashdeep sir to please start the session on the topic use cases in Neo4j.
Yeah. So you are able to see the screen?
Yes, sir. Yes, sir.
Okay. Okay, so let's look into recommender systems. Some of the industrial applications of recommender systems. So starting from all the major, any trillion-dollar corporation whose market cap is trillion or approaching trillion, they all are using recommended systems. Okay. Now the only open source thing that you can keep in mind, representation centric application is from Leipzig University of Mannheim, called DBpedia. Okay. So on and so forth. Now what are the use cases? So data search, okay, Google search, PageRank I had already told earlier how they're using our geolocation also, providing us more nearby information priority over most highly backlinked resources in the internet. Even if there is a highly backlinked resource in the internet, it will not show up in our own search field. So to get the most relevant technical information, you might consider using VPN also. Anyway, virtual private network. Similarly, Microsoft also data search. Okay, Wikipedia is using knowledge base for their data. Leipzig University is doing semantic query. Okay, so there are different use cases. Airbnb is trying to contextualize. Okay, contextualization is an amazing use of recommender systems. Okay, one of the not so good for consumer but very good for the e-commerce vendor. If you search for a marriage wedding dress in the same top white color and same vest and all the other accoutrements in the dress, they will be sold to you at a 35% premium. So that is one use of contextualization. Depending on what is searched, the same item gets a premium price tag. Likewise also, the other opposite is also true. Okay, if you put something in your cart and leave it, then a coupon will be auto applied so that it will become cheaper, and that coupon will usually expire in some hours. So this is another contextualization use. Okay, cart, is it in the cart or not? For us, a cart looks like a graphical thing. It is separate from the search bar. But for the algo, it is all part of recommendation. Is the property field in cart equal to yes, no? Okay, and is the buyer capable of buying? See the purchase history prior. Okay, then apply a incentive, apply a coupon. So this is all recommended. Looks real time to us, and it is almost real time only. So that is the power of contextualization. Okay. Let's see why I'm telling that a computational threshold or computational bottlenecks come with SQL. So if you have a SQL query, okay, look, this is Peter, he's a user, Johan and Emil, 3 users, okay. They're all following each other. A linear growth of data entries results in exponential growth of data connections. Graph database promises higher flexibility compared to tabular database. So this 3-node diagram in SQL, you will need multiple joins. Select name from person field. Okay, then left join, make a new entry or something. Okay, call it person department. Then on person ID equal to person underscore department dot person ID. Okay, so you have to keep doing several joins like this. Again, do a left join on the department, on department ID, person underscore ID dot department ID. Okay, where department dot name is equal to IT department. All that join, you can say goodbye using what? Using any not only SQL variant in graph query language or cipher query language. Here, what you have to do? You have to do match p colon person. So you created node person. Okay. Works at, you create a relationship d underscore d colon department. You've given the other node. Then where you will put the d name equal to IT department. Return p name. That is all you need to give the query for knowing who works where. So content-based recommendations. What happens here? User will be recommended items similar to the ones the user preferred in the past. Okay. Item 1, 2, 3, item n. What is happening is, if your user in your app is changing without changing the login, that often happens, right? Our family members will take our Amazon account. In one family, not everybody wants to take Prime subscription. So whoever has the Prime subscription, everybody will order from that Prime account. So what will happen? The recommender will recommend for a male also, for a female also, for a young female also, okay, for an elderly male also. So then this kind of recommendation system, which targets content-based recommendation, usually is insufficient. In which case, the user itself can keep changing without the system knowing. For the system to know, you would have to log into a different Amazon account. Then you'll have to buy Prime again. So oftentimes what they do is they do MAC ID also to understand that even if the account is the same, is the MAC ID also same? If not, then they will flag you as a different user in the same Prime subscription. In India, they are very liberal. In America, my friends are not able to do that. Everybody needs a separate Prime account per MAC ID, usually, unless it is a cluster of, let's say, iPad and iPhone and MacBook. Unless it's a cluster of the same user, same person. But how to know, right? Even if it's the same person, anybody else could be using it instead of the login. That is one of the inherent limitations of recommendations based on content in the practical world. Okay. So next is collaborative recommendation. This is what all the LinkedIn and Facebook and all the other active social networks, this is what they will do. They will see what is the, what are the people around you doing. Then they will say, look, this guy also bought this. Or Amazon will say, users who bought Neo4j, recommend them to something else. By the way, if you didn't know, there is a Neptune called a service called Neptune from AWS. Okay, if you don't want to get into the headache of how do I host my Neo4j instance on the cloud, for that, Amazon has created their own graph query implementation. This is Apache related query database. It is not Cypher query, so you will have to relearn some of the mappings. However, it is also a key value property based system, and once you get the hang of it, it will be like a Marathi speaker picking up Gujarati, or a Telugu speaker picking up Kannada. There will be some differences, but many things are similar. And this Neptune service is relatively new. Okay, it's not too new. If you say Neo4j started 20 years back, compared to that, it is new. You will see ample documentation from 2019 onwards in Neptune. But here, all I'm saying is go to AWS and book a Neptune SaaS app. Okay, just search neptune.aws.com. Go there and then you can start deploying graph on the cloud. Alternative is, if you want to just work with Neo4j only and you don't want to relearn the mappings of Neptune language, alternative is you can go to Neo4j, then go to Sandbox or similar some pages there. Then you can find their deployments on all leading cloud providers. However, any convenience will come with a corresponding fee. So if you see per instance basis, because AWS is the largest data solutions, data systems and data center provider, there is no continent other than Arctic and Antarctic where you will not find AWS availability zones, they call it. Because of that, AWS is able to offer you significantly price attractive dollar per compute. However, what happens is if you go with the AWS people, then you will have a hard time reconfiguring it and pulling out of the system. So you will be system locked. You will be dependent on them. So whensoever they say that Neptune will now be costing 2 times more than before, you have no option. You have to pass on that expense to your users, to your customers. Okay. Let's see. Collaborative filtering is all about all the people around you, what they are doing, similar recommendations, similar things you will get. Okay. Then so movie recommendations. One of the key takeaways that here you can understand is all the faculty members who are attending, they should feel that okay, they can explain this graph database better than me. That is one of the key takeaways. If you feel that way, means one of the goals is achieved. Okay, simply because this topic you will have to go step by step, but then you will not be able to cover the breadth of it. If you go for breadth, then you cannot wait for code execution and people giving their feedback and all. So running a remote lab is currently a challenge. This challenge also some startups are addressing, like Gooby from IIT Madras. Okay, let's come back to the recommender crash course. So some code I have given, we'll get back to it later. I want you to see the implementation of a data scientist from Aspen Technologies. We'll see what she has done. Before that, I'll give you some more background about the recommenders. So the user preference is implicit and explicit. Explicit means the like button in Facebook. Okay. FD, YouTube, all those likes. And implicit feedback is a little more delicate. You can see this through click responses on the website. There are special tools that will do hotspot mapping or cart abandonment that I had told you. So the user's behavior you are correlating not by asking them explicitly, so that is why it is called implicit. Okay, you're taking it without explicitly telling the user. So then you take all these inputs. Where does it go? It goes into your recommender system. Then it will generate recommendations. Right. This is what we usually think, right? Actually, what happened? There's one more thing. See whether the recommended output has caused desired action or not. If not, then flag the recommendation with some kind of new key value pair. This is the implementation aspect that a lot of people are not able to gauge, because this is something that the user will do with your system. You cannot early on predict it, but you need some kind of system to track what the user has done and then associate it with your recommendation. So let's see further. In collaborative filtering, similar users like similar things. Okay. Then one of the things that we need to know of is also normalization. Okay. So why normalize? If you don't normalize, then the extremes, okay, the 0 givers and the 5-star givers, Actually 0 is not available, 1 star is available, so 1. So there are people who will tend to give 1 to 2 all the time, then there are people who will tend to give 4 to 5 all the time. The really optimistic people and the really pessimistic people. So if you don't normalize and your whole data set is full of such extremes, it will be hard to make any kind of basis. Okay. So you need to normalize ratings by accounting for bias. Some people are so biased that if they see their favorite celeb, they will give 5 star, 4 star, irrespective of product quality. Likewise, also, some people don't like that celeb. So because of that celebrity, irrespective of quality, they will give 1 or 2 star. So bias can cause all these kinds of skewness. So you're trying to fight bias by normalizing. So one of the ways to normalize is mean normalization. So what do you have to do? You have to subtract a term from each user's rating for the given item I. Okay. So what does that equation feel like? U of I. Okay, this is the user item rating bias. Then what does that depend on? So what is the global average? And item's own average rating. See, if something is inherently useful, then a large number of people will say it is useful, right? At least that's the rationale, which is BI, okay, plus BU. Okay, what is that? User's average rating. So is the user always giving 0, 1, whatever? Irrespective of that, even the most pessimistic user would sometimes give good ratings, right? That is one of the ways to counter the bias. There are many ways. This is one of the simpler ones that I have put. So what else we can look at now is so you've done the normalization. So you need to do a model selection now. Matrix factorization is common collaborative filtering, collaborative filtering technique. So there are two parts to it: user factor and item factor. Similar to bias, but this is a little different. So what we are trying to do is factorize the user item matrix to get two latent factor matrices. User factor matrix. This is a matrix, okay. This is a matrix. User item. And what is this other term? That is also it's going to depend on what? It's going to depend on the user and the item. So what will be happening to the missing ratings? Missing ratings are predicted from the inner product of these two factor matrices. So this is x of mn, okay, p of nk into q nk raised to t is equal to x hat. This matrix factorization also is amply documented. You can find a lot of reads on that. Now these and all will not sit and manually code, right? Why to sit and manually code? There are so many resources to implement it, already implemented as algorithms. So which algos will do matrix factorization for us? There is alternating least squares. There is a stochastic gradient descent. And there is singular value decomposition. So each algorithm itself was once upon a time somebody's major research paper, PhD thesis. Going into detail is kind of way outside of this current session. One last thing I'd like to bring our attention to is precision. This is a valuation metric. Often addressed as K in literature. So what does it mean? It could be like of the top 10 recommendations, what proportion are relevant to user? Okay. Now let's just look at what the data scientist Julia Zozuli has done. So she has worked on the movie database. Okay. And as you can see, this small sample, 12-year-old, 12.5-year-old sample, has mapped 610 users. And there are 100,000 ratings for nearly 3,600 tags, 9,700 movies, and so on. So if you want to see all the categories, you can look them up. Okay. They look like all these musical, comedy, crime. This is all you will find in the dataset. So the dataset is shown in the earlier slide. It is in the TMDB dataset. That is, they give you an API, the moviedb.org. So from there you can find the dataset. Other parts of it is from movielens.org. Okay. So beyond the category tag of the movie, genre of the movie, what we have to see is the ratings. So what about the ratings? Like a lot of other recommendations, it is from a 1:5 scale. Here the main thing is compared to e-commerce, more granular, 0.5. You can give 0.5 increments to your ratings per movie, per user. Usually in recommendation, you will always find per article and per user. This is always there. These two are always there in the most recommendation systems. For Google, it will be per search term per user, something like that. The user is represented by ID. Why? Because GDPR. You start giving everybody's name behind all their behavior, then the world will come to a stop. So there is going to be only ID, thanks to GDPR, privacy laws. And that too, the user ID is also anonymized. So even if you have this user ID from somewhere on the movie database, TMDB or Movie Lens, you still cannot figure out anything to do with the person. These are anonymized. Meaning you can just hope that the database that you gotten is proper enough that user IDs are unique. That is the only expectation we can have. Other than that, user IDs are basically random numbers. Tags.csv. So what is here is each row of the file tags.csv, and at the end I'll give you the GitHub also link to this excellent work. You can also start incorporating. And another alternate method also you will see in the session later on, where you will not even have to download database. Everything is offered to you by Neo4j. So each have their own plus and minus. Okay. We'll first see in the current case tags.csv. What does it represent? It represents one tag applied to one movie by one user. So these are the tags. So each tag has been applied by a user on a movie ID at a given time. So tags are user generated metadata. What is metadata? It is data about data. Anything where you see meta, it means something about something. Okay. It is not the actual data of ratings and users and articles and all. It is a data that is a descriptor of their data. Tags are user generated metadata. Anywhere you see this term user generated, there all the investment community becomes interested. The more you can engage your user, the more you can improve your valuation. So TMDB 5000 data set. So here you are like in this case the scientist has done is there is a movie database API, TMDB API. From there you get a compressed file, and for in our case it was like this. It was TMDB underscore 5000 underscore credits dot CSV. You can have different names. Okay. Similar things you can also find from kaggle.com. Okay. Each row of the file will contain, as you can see, all these JSON key value pairs and similar tags and all. So there will be movie ID, title, cast, crew, and so on. So here only the actors' names from cast column and directors column, that director's name from crew column has been taken. So cast, actor, and from crew, director. You can choose different things depending on what you're trying to analyze. Now each cell, there is this kind of JSON information. Okay. Each cell. In addition to that, there are two more CSVs. Okay. Information about budget, genre, original language, and so on and so forth. Movie credits. So who are the people responsible for the movie? Only one of the two was used in this case. One alternate snapshot of the database. So this is a very popular film. So much information goes into a film, and we as consumers never even bother. But that film has created so much employment and so much data. So when we come to the data science side of things, then we start looking at, oh, all these things are involved. Is it? Let's read the data. So movie lens part, dataset part, you can easily load it in Neo4j using the load CSV function. Load CSV, and it goes into Neo. How does it look like? You will use the merge clause, then you will use the for each clause. Merge what? Movie, okay, id line.movie.movie id, okay, line.movie id. This you see, if you go to the movie lens dataset, it can be that your mapping has changed. So you have to see where movie id is and what is in front of it and all that entire thing. You have to take it and you have to map it to id column. Similarly, id property. Similarly, title property, you have to give line.title because the dataset movies.csv at that time had it. Now if you get it might change. So for each, so g name in split genre name, okay, lines.genre, use the pipe operator. So this is the separator here. If this separator is there, then you do the split operation. Then you merge what? You merge the genre that is in the g name, you merge it, okay. This is going to become the key value pair property of what? Of the G node, okay. And G node can also have genre noble and label. Then merge something more. So merge a relationship now, okay. M movie and genre relationship is genre. So I would advise you do this in the browser so that you can get access to more and more epoch functions. Then match, when you run the query, what does it look like? So it will start generating these kind of relationship graphs. You see, all the ratings are the relationships. There is also another query that you can do for ratings. We'll come back to it later. If you run this, then you'll get the relationship between movie and genre. So where you have to place it is important. I think you have seen this from our first session lecturer, Shri Gyan Prakash sir. You need to place them in the import folder. One of the things that you could see is, are you the admin? Okay, do you have admin rights in that folder? If not, then when you install Neo4j, try to install it in a drive in which you have admin rights. Okay, these are all things, OS related things, can stop you from accessing the thing from within Neo4j. Now let's download, means once you've done that downloading, creating label, movie with properties ID and title and label, then genre, and so you'll be able to create the mapping. So data reading and pre-processing. By downloading data from ratings.csv, we all can create label user with only property ID. Data about users are anyway anonymized now. So that property ID is all we can give it. Connection we have to give is rated with the property rating, user rated, then you put the rating in the curly braces. Okay, then you give a directional mapping to movie. Something like this. Load CSV. This load CSV not every time you need to do. Okay, first time when you are getting the data inside, you have to use. Then you have to do match. So you are creating movie ID and you are merging it. So you see, you have already created movie ID, right? Each time if you keep merging, doesn't make sense. So you must call that already created M. Okay, movie. Then you merge it with user. And you have to create, no, you're not merging it with user, you are creating a user node using merge function. Then you are giving the relationship using merge between the user and movie. User and movie. What is the relationship? Rated. Okay. Similarly, you can do it with tags also. Match movie. Okay. Recall all the movies that are already entered in the database. Then you have to again match user also. Then you have to say user tagged what? The movies. So you are creating this relationship, directional relationship. So what happens is all those labels are applied, 610 labels across nodes, then 100,000 properties, and another 100,000 plus relationships and so on will be completed in whatever time it takes depending on your processing speed and all. Similarly, you can see tags will also create some additional properties and relationships. Okay. Data reading and pre-processing. So links.csv has three different IDs of each movie. Movie ID, which is coming from three different IDs. Okay. One is coming from movie ID field. That is a movie lens dataset. Another one is coming from IMDb. So it is called the IMDb ID. This is coming from IMDb. Then TMDB. This is just called ID. TMDB ID. TMDB. So using that, can we get information about actors and directors of movies? So can we add to each movie new property? So then load CSV. Then you look up the movie ID. Then you can set. So what set does is it allows you to update. TMDB ID is a part of, okay, you're setting this TMDB ID to be part of your movie. And what does it correspond to? It corresponds to line.tmdb ID. So you've also heard from Gyan Prakashji there are drivers for Panda and all that. So if you import pandas as PD and import JSON, what you're trying to do is basically so the content is huge, okay, and it's not easy to download to Neo4j. I mean, it's easy, it's possible depending on what is the specification of your nodal computer. If you have a very powerful 32 core machine, latest from AMD, then it's not going to be a big hassle. Otherwise, for laptop users, it will be challenging. And all that information at one go is a headache also. We can only see a huge jalebi cluster of dots. We cannot make sense. So what can we do? So we can start prioritizing what we want to look up first. Okay. Information of director of photography of and casting director to make a recommendation. Director of photography of casting director. Okay, that's a very convoluted search term. But actually, in Hollywood, where productions are in the hundreds of millions of dollars, there are so many assistants to assistants to assistants. So there will be the first assistant, second assistant, third assistant, fourth assistant. All that data in the crew is not even ever going to be registered by we, the film user, film viewer. But the data set will show everything. Because that is the aspiration of a man. or a woman also, away 8th assistant or umpteenth assistant, that their name will come in the crew list, and then from there they will try to move up the ladder and be the first assistant, and then eventually the director of photography, and so on and so forth. So all of that assistant's name will be there in the cast. So we got to filter out and create a file that is easy to read on the constraints of our local node. So one of the ways is our good old handy pandas, sorry, not the blue panda, the pandas from Python. So you are going to use the import JSON. Then data is equal to pd and dot read underscore csv. Then point it to your directory, okay, in your desktop, whatever where it has come, and you read that. And then data dot head. So then you start getting look at all the headings that are there, and you will also be sure that okay, your machine is able to at least read it inside pandas. Otherwise, you have to switch your machine. So let's look at the JSON. Every time you work with the database, some JSON will always show up. Here we can see that character Jack Sparrow, credit ID. Credit ID means credits is all the people whose effort went into the film. So credit ID isn't part of that credits CSV file. Nothing to do with credit card. Gender. Gender is 1 or 2. Okay, that is how this data set is showing. And ID. And then name. Name of the actor. So this and all you'll find in various capacities for different people. And now if you want to extract from the cast column something, then you say cast df data frame. So df is something you create, so you can call it anything, you can write whatever you feel comfortable, is equal to pd dot pandas data frame movie id, and so on and so forth. You have to give this kind of a syntax. So for index row in data enter rows, movie id is equal to row movie id, and this is coming here. Then c is equal to pd data frame dot from dictionary, good old handy dictionaries, json dot loads row cast. So this row cast, so they're going to put this cast somewhere, something from this, okay. And then for index row in c iter rows, so this is some kind of a, they're doing lookup. So they're doing this lookup in this for loop. Then cast df location length cast df is equal to string movie id row name row character. So cast df, they're going to try to figure out the count of it all. Similarly, movie id, role, person id, all this data they are trying to extract from Python. So actors also there will be so many. Outside of the key actors, can we ever recall who all the other supporting staff are? Very rarely, unless the supporting staff is some kind of a comedian. Very difficult to have recall of all the supporting cast. So, and that too, many of them might not even reappear in subsequent movies of the same main actor. So one way to do it is remove those who played less than 5 times, because probability of people who don't even show up 5 times in the entire data set in order to make a recommendation is very, very low for making helpful recommendation. Okay, so this is what we can do is we need to count from class df, and you need to use a group by person name, and then person name you want to transform under series value count. In class df, is the count greater than 5, put that in class df. Then do a drop, okay. If count and axis 1 in place true. Then cast df count. So only 33,000 actors were selected out of 106,000. 106,000 have played less than 5 times. Similarly, cast is people who play in the movie. Crew is people who are responsible in the background also. So crew also there is a JSON data set. Then there also similar data munging we need to do. Department camera, director of photography, then department writing, job novel. So name is J.K. Rowling, David Yates. So J.K. Rowling donated quite a lot of resources to us. Good person. Then director DF PD.data frame to us meaning to the country. Okay. Anyway, so director DF PD.data frame movie ID person name. Okay. Then run a for loop. Row in data dot interrows. Create this. So look up this in this and then see if movie ID is movie ID. Okay. This is from your data set movie ID. Like credit ID, there is movie ID also. Then for looking up crew, you have to look up crew. See here there is crew. Okay, not in this, but in the data set there is. So look up that crew. Then see JSON load 0. Wherever it says JSON, that is coming from JSON. Now, if crew is not empty, then name list crew. See the job. Is it director? Only match for directors. Okay, in the name. And then if length of the name list is greater than 0, director df dot location length of director df is equal to string from movie id name list. Okay, this is an array. So initially using it at 0 and whatnot, and from there it will start going for further director df count. Further director details. And similarly, director details. So in director details also, just a minute. So extracting the information about directors, director df panda pd dot data frame movie id colon square brackets comma person name so on, and then another for loop index row in data enter rows so on. Okay, so all this we are doing so that we can, like with the actors logic, we can discard those directors who directed less than 3 movies. Okay, then just a minute. Then you have to run a subsequent code to prioritize it, count greater than 3. Okay, and then it will update the count again. So data frames to CSVs. Okay, we are trying to write these data frames back into CSV. Data frame is only inside Python. With that, you cannot work on Neo4j. So you have to again write it to comma separated values so that you can take it to Neo4j. Basically, you just do a to CSV and you write it. How it will look? This file it will look like this: movie ID, person name, role. Movie ID, person name, so on. Now we can go back to Neo4j and read it. So load CSV with headers. Okay, from director.csv. Then match. Match is like a lookup. Okay, so inside a movie table ID line.movie.id, then you merge it with person line.person name. Then you can merge it. Okay, person name is related as director of movie because we are trying to create the nodes directed. So director directed movie like that. So like that, 339 labels created, 339 nodes, director nodes. So 3 or more movies minimum they should have directed, right? So that is how we brought the number of directors down to 339 and so on and so forth. So load CSV with headers from file CSV like roles.csv as line. Then match the movie. Okay, this is very similar to the earlier. You can see. Then you have to merge. This merge is like you're creating. Okay, you already created, do not overwrite. So you can always go bindas with merge. And here what you are saying is you are going to create using create function acted in. So p acted in. Okay, and then you are going to set what the role was inside this r dot role. So you're adding role information also, updating role information also. So this is how it looked for this implementation. Okay, building recommendation. If you want to see how it looks like, you always have to be careful. They say no, be careful what you ask for. You will get it. So if you just bindas go and enter return, then you'll get the entire whatever thousand number of movies are there. Everything will cluster your screen. 60 inches screen will also be small for that. So start filtering down. You want to go from one movie, you want to traverse your graph from one movie, pick a graph, pick a movie, right? So this movie is in this case. Instead of that, it could be article in a e-commerce store. If you want to start traversing your graph, okay, I'm saying that it need not be movie all the time, okay. It could be the e-commerce article. How many people are buying Steam machine nowadays? Okay. Otherwise, for Netflix and similar OTT platforms, how many people are watching cricket nowadays? Not cricket, then what? Some latest movie and so on. Sometimes the novel name and movie name will differ. So that information is also there. So that also they are trying to use here. Now acted in is genre directed. Return MP. So acted in means all the actors will come. Is genre means what all genre related to Harry Potter, that will also be shown. So see, these are all the genres. This is our chosen movie, traversal starting point, and directed. So see, directed. One movie cannot have too many directors. In fact, there's only one director. Everybody else is an assistant, and an assistant to an assistant to an assistant. That is one thing we have noticed. Okay. What next? So if you want to, let's say, look up something else. You want to find out the second degree, what to do. So again, call that traversal starting point. For us, it is the first movie in the series of Harry Potter. Okay. Then all you need to do is this magic. Star dot dot 2. Then it will show everybody who is having second degree connection to director. But if you don't call the actors here, then you'll not see actors. So each movie anyway has one director, na? So you have to be careful in your dataset schema design that you need to call the thing that you are looking for. In this case, you can only look for the actors because we have not called all the other crew. That is the design of this schema for simplicity. Your schema need not be that simple when you are going to real world scenarios. Then if you return, then you will also see your 15.16 screen is too small for all the people, all the actors who are even second degree connection. Sometimes, depending on dataset, it may not be, but usually it's a good practice to limit how many findings you want. Okay, 50 is also too cluttersome, reduce it to 15. It's up to you. Then you'll get something like this. Second degree connections. So a lot of names are here. Okay, let's proceed. So if you want to find out who liked what in this anonymized world, what can you then use? You cannot look up users by names now. So you have to use the tagged feature, tagged relationship by using the pipe operator. Rated or tagged. Whoever has given these properties from the user family, okay, user label, please come. And if you don't put limit, then again your screen size will be small to show all the data. So with 25, this is how it looks. These all numbers are users and none of these numbers are real. I mean anonymized. So it's okay. Then this user is generous enough to put tags, genre tags. You can see out of this small sample of 25, only 2 users are bothered to give genre tags. Rest all are happy giving number ratings. So you can find out such questions. I mean, I didn't have a question to know who is giving genre tag, but the graph revealed it to me. So when your graph starts giving you insights that you didn't even ask for, then you are gradually uncovering things that you didn't even know you don't know. Of course, there are far more sophisticated algorithms and cutting edge research to increase the occurrence of new findings. So, we are a little familiar with data. How does collaborative filtering look like inside this graph dataset? So let's find the movies the user likes, then find users who also like movies like that. Okay, so one user, targeted user, okay, one traversal point starting, okay, one user you select randomly, any user to traverse your graph, and depending on that user's likes, find the similar users who also like that movie and they recommend that movie. Okay, and others are liked but which our user hasn't seen, rated, sorted by number of paths that led to a particular recommendation. Okay, let me just make a note of it. So you select your traversal starting user, then ask who all also liked these fellows likings. Okay, this fellow has rated something. Who else has rated that favorably? Got it. Then recommend movies that other users liked, but our user hasn't seen. So this fellow hasn't seen, not rated. Sorted by number of paths. Sort the whole thing. That led to a particular recommendation. So what is the query looking like? So consider a user me, give it a starting point. This is your graph traversal starting point. Then give it a relationship, directional relationship. This fellow is rated. Okay. And it has rated something from where? From movies. Who else has relationship to movies? Other user. So what you will do? You will draw an arrow like this on paper, right? So inside uh, Neo4j, this is how it will look. Always remember, whatever is here should not repeat here. So they have to be unique. Then what? And similar things also I want, okay, from a third person. Other user R3 rating of movie. Other condition, if you want to append, you use the where clause. Consider it like a condition appender. So more things you can append to the above thing. Now I want to prioritize the ratings, isn't it? We said sort number of path. So you give a priority. R1's rating, if it is greater than 3, and R2's rating is greater than 3, because we said like, we didn't say dislike, we didn't say just rate, we said like. So to make the liking noticed, only look up the ratings which are greater than 3. Only look up the ratings which are greater than 3. Again, only look up ratings which are greater than 3. Now this is set up by you. You could have said 3.5. Generally, the higher the you go upwards in scale, even inside Amazon and Flipkart and all, if you give average rating greater than 4, something kind of a skewness will come. What will come? The number of ratings of those articles is less. Try it and see. If you give average rating greater than 4 or greater than 3 and compare. So number of ratings per article goes down as the rating goes up. So what I'm saying is More users, there will be greater likelihood of 1 star, 2 star. So the rating coming down is usually what I've seen. But these articles, they have more number of ratings. So like this here, 300 ratings will be there. Here, 30 ratings will be there per article. Why? Because the vendor itself will ask his neighborhood people to buy his thing and give 5 star rating. Na? The 5 star you'll find in very few articles. Something like that. But here we are not being so fussy. We are saying anything above 3. And me. So the graph traverses starting point user 220 must have also rated. Okay, so that you want to relate it to M2. Sorry, I just said the opposite. It is and not me. A very important thing. Okay, remember, we are trying to figure out things that this fellow doesn't know he can like. So and not me. Then return. Then what? So this is kind of like a constraint. You can set this constraint. So return distinct M2 as recommend. So we saw in that earlier case where we had directly used that epoch function that we were always using this as tag again and again, right? So this is one of the common things you can do with the as tag. You take something and you want it renamed as something, use the as tag. Then you want to count something, then you want to put that count into something, then use as and put it inside score. Then you want to do what? Sort. So this distinct thing, more than a constraint, is actually sorting for you based on the number of paths. So this constraint are not to be limited in calling it constraint, but it is actually working on the number of paths. Okay, so this is what this is going here. Distinct. And then you have saved these. Then you're going to order by. You have seen order by earlier. You're going to order by score descending. And of course, whenever you are asking for results, ask a limited number of results first, and then you can keep expanding if your screen size allows or any other metric. Yeah, so the outcome here is a table like this. So for Mr. 220, he likes all these scary things, Silence of the Lambs. Actually, this Silence of the Lambs is scarier than almost all the other movies here. Something to question then. Why such a nasty or a scary horror movie has shown up? Anyway, let's move ahead and see. So in this collaborative filtering exercise, you've used the users who liked something common to your starting point user, and then you ended up recommending things to your starting point user that your starting point user did not rate. Now what else? Every user tends to give more higher or lower ratings in general. So that is why that average rating of particular user is better. See, earlier I told you about normalization. You remember? I had mentioned normalization. There is an equation and you're taking averages. So that same average also you can use here. Rather than hard coding that 3, why not go with the average? So that is why here you will see average, not number. Then again create relationships. This line is very similar to earlier line. Next line, we are sorting as per the average. So keep writing average everywhere. So you already stored AVG of rating. So see, this average is not a keyword inside Neo4j. But if one time, sometime in the future they make it a keyword, then you can always call something else here, right? You can call this EAV11, whatever you want to call it, AVGE. So this is up to you what you want to call it. Okay. So you're going to put the averages and then you're going to start creating constraints where a bunch of people have had the same thing. Bunch of people have had average rating. So R1 dot rating greater than average, R2 dot rating greater than average, and so on, R3 dot rating greater than average. And not me, not your starting point user. How he is related? Rated, colon rated. With what is related? M2. Your movie set. So return something. Return distinct M2. So we're trying to find that path again. And you're ordering it by score descending. So what you want to put in the score? You're going to put the thing you had seen earlier. Sort the number of paths. The number of paths. So that you're going to put inside the score using count function. So return distinct M2 as recommended movie. Okay. Count star. So count the number of paths as score. Then order by score descending. Limit. Again you can set how much limit you want. So that way you can see, is there a difference? Some things have changed, some things are similar. See, alien was at the end, alien has gone to third last. What else has changed? Lord of the Rings, LOTR is in its own place. Schindler's List has gone up. This has also gone up. So some normalization will give you different outcomes. Now we saw it in the form of a table. This is our score. Can we also visualize it? Yes, we can. Anything major changed? Not exactly. Just click on the tab for the graph and you'll see it. So this is our 220. He liked office space. Okay. And 282 also liked office space. But 288 also liked a whole bunch of other things. Which of these from this whole cluster we want to send to? 220 is a recommendation. That is what we are trying to understand by this query. Okay. So can we use some more metadata? Data about data, metadata. We can. Using tags. Remember at the very start I had given you what is an implicit and explicit indicator, and Facebook likes is a explicit indicator. So we have seen that if we set an average threshold, we will get rating into likes. We will be able to say which ratings are the likes. Find other movies with same tags, not taking into consideration whether other users who describe other movies liked that movie or not. Here now, if you take a step back and just question, okay, given the kind of tag is associated, okay, what other movies and tags could be of our users liking? Actually, more than could be, actually are rated by our user as liked. So You are getting a. We are going to take a look at a different user. This guy is number 318. Change your graph traversal point. No need to fix with one user. Then relationship rated with a movie. Then taking your starting point user as your core. Figure out the average rating. Store that inside a variable average or in a tag or some whatever, you get it right. This is your placeholder for the rating. Then match me with match means here you are going to create some relationships, right? So tags, you're going to see the tag. What did the user 318 tag? And he's obviously tagging a movie. Okay, what is the relationship of the movie in terms of ratings with the user? So that is why you are saying me on both ends. What is different is relationship. Then match other user. If you want to see their tags, you must keep it as a different name. Okay, don't overwrite it with the same thing. T2. And what it is going to relate to movies. So M1 colon movie, where the rating is greater than average. This is your normalization threshold. Plus you're going to add more constraints to it. So then you can go ahead and and it with what? Tags. Because we are talking about similar tagging, right? So T1 tag, T2 tag, and not me. Okay. So things that I didn't tag, that also I want to see. And you'll bring it all into M1. And again, not me, rated M1. Return M1 and other. Okay. Something like this you will see. Well, actually, if you run this code, you'll see what is on the next page. But to bring to your attention, it will be a very dense graph. Why? Because in the limit, you have not, a limit is missing. So there is no limit. So it will be a very dense graph. It will be in the next page. Slide. So this is how it will look. This is how most modern day graph databases are. Subgraph showing movies liked by above user. So in the collaborative approach, let's look at actors which our user liked. So there are multiple ways to like a movie. You can like the movie itself or you can like an actor. Users could, but here usually we are talking about movies which our user liked. Okay, let's find the actors. So then can we say that the other movies in which the same actor appeared, can we recommend it to the user? So that is the question we're trying to phrase out here. Sorted by number of times particular actor appeared in such movies. Number of times particular actor appeared in such movies. So what we are trying to find is actors where to look for them. So user liked movies. And then we are going to sort by number of times particular actor appeared. Actor appeared in liked movies. So giving the same 318 user, then connected with rated and movie, match it. Match it. You're looking up the current cluster, so you're matching that, and then inside that with me, taking average rating, store that in your average placeholder. Then you again match. What do you want to match this with? So this part you're going to see, you're going to bring in acted in, and acted in, all those acted in are stored under person, so bringing that also, where rating is above average. If the rating is above the average score of the r dot rating, then it is something that was liked. This is how you're getting the liked, deriving the liked. Okay, don't consider it as a syntax, just writing it down here. Then return p as actor, count as score. This we have done earlier also, count as score. Then order by descending and limit the number of entries to get this kind of a table. So we have told it to count number of times p as actor has occurred, so it has counted, and from 10 onwards we are limiting it to 10. There could be a higher thing, you decide, right? So from 10 onwards it is coming. So Johnny Depp has occurred 10 times in movies that have been liked by 318. Similarly, Matt Damon also. So it can be that Johnny Depp and Matt Damon movies that 318 hasn't rated yet could be the new recommendations for 318. So can we illustrate this? We can. This is how it looks. 318 in relation to 4-star movies. And we do the same with directors, where we can look at the directors that are commonly appearing in the ratings, in the above average ratings or the liked ratings of 318. Let's see. We can do that with directors. What do you have to change? Here, when looking up from the person's category, we have to look at directed. Earlier, what was it? Earlier, it was acted in. So, if you look up directed, then you are going to end up with P as director. You have to return P as director. This P you want it named as director. So that is why you are saying P as director. Then count as score. Then it will come under name score. And order by descending, limit to 10. So the top 10 are come. Can we do that for genre? We can. What has changed here? We cannot use P as person anymore. So you have to see, look up for genre. So you have to see P colon genre. Then the relationship cannot be directed, it has to be is genre. So then you can see for above average rating. This is our normalizer. Then you return here P dot title as genre. So you are going to take that part of it and you are going to put it in genre. Then count again, you are going to put in score, and again you are limiting it by 10. So these things are changed. So 318 likes to see drama and comedy. According to genre. Followed by thriller and action. Category 18. If you want to bring everybody together, how to assign importance? Oftentimes, if you want to solve the importance assignment issue, whether it be neural networks or other aspects, weighting is a common tactic. Okay, so we will assign weights, combine information about favorite actors, directors, and genres to provide user with weighted recommendation sorted by number of overlapping paths. So this is some new thing that has come. Number of overlapping paths. Because if you are going to put so many people there, so many nodes there, overlaps are bound to happen. Sorted by overlapping paths that lead to particular recommended node. So you've already done a lot of things, nothing to be worried about. All you have to do is, when too many people come together, you have to start being careful about weights. This is the thing where you have to see how the weights were applied. We want to score, we want to take hold of the weights. We want the genre score, actor score, director score, GS, AS, DS. This entire line is just to make it beautiful. The actual thing is here. Parameters or weights that you have given. Okay, I want to bring this down, I want to raise that, I want to bring this down, I want to raise that, then that number here will be a fraction, here it will be a multiple. Okay, then that weighting will be 2 skewed. Generally, you catch the drift. Something multiplied by 5 will be more important than something multiplied by 2. So on and so forth, you decide what weights you want to give. For demonstration here, 5, 2 and 5 are taken. Director and genre is given more priority than actor. That's what this is saying. We are taking this entire thing and we are going to put it as weighted score. So here weighted score. So let's see. This is also 5. This is 2. This is also 5. So this is a weighted score, right? So 5 into GS plus 2 into AS plus 5 into DS. So is it happening? If I multiply by this by 5, I am getting 25. This is becoming 22. This is 0. So 22 plus 25 is 47. So it is happening. So we are given a weighted score. What else is different? You are going to put count value of the liked movie. First, you are going to put things that are in these 3 categories, and you're going to see which is count. You're going to count for that, and you're going to keep it as genre score. So wherever all genre has come, wherever all genre has come, genre score. Put it inside GS. Then you are going to count the number of actors, put it inside AS, count the number of directors, put it inside DS. Okay. This is person can be acted in movies and also acted in recommended movies. So that is why there is an optional match. Again, here also a person can be directed in recommended movies also, but in the larger set of movies also. Okay. So with your traversal starting point, look for the movies data set, recommended set, the genres which have been counted, then the actors that have been counted, and lastly, see here we are putting this GS, then we are doing the AS, and we are bringing AS also, and ultimately we are counting the DS, counting the number of directors, and then we are bringing them into DS, and then we are calling match where not me rated RM. Return RM title as recommendation. So these guys were not matched or liked by 318. If it is already liked, what is the point of recommending? Okay. Then this score I had done and shown you. This all line is to beautify the table. Then how to order it? Weighted score. So you are putting all of this as weighted score and you are ordering that table based on this column. So you are going to use this with the descending function. Order by descending. That's what you have done. Order by, then you write the thing that you want to order by, and then you write DSC all caps, and then you decide how much results you want printed out. Limit 10. So that table, whenever you have a large table like this, visualizing is going to give you khichdi. You don't want too many things. This is also a lot, but still, if you want to reduce the number of returns, okay, then just show me recommended movie. Show the graph starting point. Okay. Not rated by me is going into RM. Okay. Match user ID. Average rating is average. This is the normalizer thing. Then again, look for relationship where you have rated, so that you can look for not me. So if me doesn't have the things, if me is not related to movies, and if me is not rated to movies, then where not me rated, you're gonna have a hard time figuring it out. So then what will you put in the recommendation? So that is why you need all this. And rating here, you can increase the threshold. Here threshold has been increased to 4.5. So then let's match movies acted in. You're trying to find the actors. Okay, earlier case we had the genre also, director also. Here we are limiting it down to actors. Actors who have acted in the movies main set and in the recommended movie set. Okay. And then match RM where not me rated RM. Then return RM actors me and movies limit to 50. Get a graph. So see, only this fellow dinner for thing has been rated by 318. Rest of them all are not rated by 318. So they can be recommendations. Not only that, these are all that have been having the actors that acted in dinner for Schmidt. Okay. Some relatedness there is, not some significant. Okay. Then one of these things we can see, this is a concept you will come across whenever you are looking at recommendations. Sorry, that was dinner for schmucks 2010. And you've seen that Paul Rudd, Rick Owens, these guys. Paul Rudd, Rick Owens, and all these guys. Paul Rudd particularly, he has done more movies than others. Randall Parr, we can leave aside. He has only done one more movie. Similarly, you can put your own hypothesis thumb rule. Okay. we have used the number of paths that have led to particular movies. Led to particular movies as a score. Now let's use Jacquard index as a similarity matrix. Okay, calculated as cardinality, number of elements of the intersection of two sets divided by the cardinality of the union of two sets. Jacquard of A, B, and this is how it is related. Okay. Intersection divided by cardinality of union. That's what we are going to use. Don't ask me questions on this because this is all coming from graph theory, pretty well documented in literature. You can get better answers from me compared to me on YouTube. Let's see how to incorporate this. Intersections in cipher. Okay, so I think I have passed the time. Is it? How much more time do I have?
Yes, sir. 5 to 10 minutes, sir.
So this thing can go on. I'll give you guys the links to the thing. It's a pretty interesting use case. Okay, I just run a last video and then we'll wrap it up. So this you can find inside your Neo4j browser and all. Okay, no need to worry. You can play with this data set. Don't need to bother about importing. This is one of the things that Neo4j gives you complimentary. You can do a whole bunch of stuff. You can create nodes and all. They are giving you all the code also, and I've also given you the code for this in the WhatsApp group. So match Tom Hanks. Okay, then similarly people as person, limit the number of people and just show them as names. So return people name. Here he didn't use as. You could have put it as a people name as actors or something, cast or something. Then what else? Then match. Take a movie title as a traversal point, Cloud Atlas. It will show you that. If you keep the return together with the name, then you want to see more, then you can use the limit tag and it will show you up to 10. Then if you want to here, we had seen this. I wanted to talk a little bit about the next thing. Here. So what you can see is 90s movie, 90s released. You can put greater than equal to 1990. And 90s released less than 2000. Return 90s title. So you can also look up within certain time frame. Then it will give you the results between 1990s and 2000. Then what are the movies? Oh man, this keeps going back. Tom Hanks. What did Tom Hanks act in? So you put this query and it will show you all the Tom Hanks related movies. Similarly, you can keep trying the queries. This is all in the WhatsApp group. So Cloud Atlas, return people, type related to, okay, and so on. So you'll get this comprehensive table. Directed, acted, anybody who's related to Cloud Atlas will start showing up. Simpler query. And then Kevin Bacon, and also we're going to use the Bacon traversal method so that you will get limited outcomes. And inside the graph, you can go and see who are the Kevin Bacon's related connections. Then this is when you see something like this star 1 to 4, then that's typically degrees of connectedness. Okay. The fourth connection to Kevin Bacon is Meg Ryan in one case. Similarly, there are other cases, other people. Okay. Then this Tom Hanks case, who are all the co-actors? Okay. Then it will show. We have talked about strength. This whole here you can see this is count as strength, order by strength, and you say descending. So whatever you have written as strength, it will come here. Then co-actor's name as recommended, so it will come as recommended. We are not Tom. So here we are trying to run a query where Tom Hanks has acted. But what are the other movies where Tom has not acted but his co-actors have acted? And then you are going to give it a strength score. Okay. So you need to count, and you're putting that count inside strength, and you're descending it, ordering it by descending. Similarly, what is the common people who are in the network of Tom Hanks and Tom Cruise? So this is Tom Hanks and Tom Cruise. Tom Hanks, Tom Cruise. They do have some folks who are in the third degree are common. Third or second degree connection are common. Okay. Similarly, run those queries and see. Have fun with it. At the end of the day, match everything and delete everything. If you are not going to use those results. Okay, I'm done. Thank you for your kind attention.
Thanks, Akashdeep sir, for such a nice presentation on the use cases on recommender system. I think participants have learned some use cases, how to apply the use cases on Neo4j. Any queries from participants? Any queries? Okay, then I can read some summary of today's sessions. So today's session 6 is taken by was taken by Mr. Gyan Prakash, and the topic is graph database and introduction to Neo4j. And the key points are: what are the graph database? What are the representation of the database, in which rows are represented as nodes, relationships as represented as links, and represented COVID-19 tracking dataset for last 3 days, and create 3 nodes: location, vaccination, and cases, and then create relationship between location and vaccination and between location and cases. Then afternoon session was taken by Mr. Akashdeep, and the topic is writing queries in Neo4j, in which the key points are basics of graph database and parts of graph database like nodes, relationship, properties, and labels, and then discuss some use cases on graph data like fraud detection, master database management, recommendation engine, and graph knowledge graph, and then write the basics of cipher query languages with examples. And then evening session again is taken by Mr. Akashdeep, and the topic is recommender system using graph database, and the key points are the basics of recommender system, types of recommender system such as content based recommender system and collaboration based recommender systems, and then creating database and use case graph data model for TMDB 5000 movie data set in which movies are recommended to users on the basis of user ratings. So that's all for the today's session summary. Now, tomorrow's session will be taken by Dr. Anmunathan Ramaiya, and the topic is column-oriented database. There is slight change in the schedule of our workshop. Tomorrow, the first session is taken by Dr. Anmunathan Ramaiya, and the topic is column-oriented database. So again, I hope we will meet tomorrow, 10:30 p.m. for the next session. Thanks.
Thank you everybody for kind listening. Stay safe, take care. Thank you, Dinesh sir.
Okay, sir. Thank you, sir. Thank you for nice presentation, sir. Thank you. So back to Parthora, sir.
Thank you, sir. Thank you, Akashdeep sir, for sparing your busy time with us. Thank you so much. We have gained a lot of knowledge from you, and hope the participants have also gained a lot of knowledge. I have seen in the comments that a lot of participants have appreciated your session. Thank you, sir, for spending your time with us. We are really thankful to you, sir.
Thank you, sir. Thank you.
Thank you, sir.
I will forward you my details. Thank you.
Thank you, sir. So we will be concluding today's meeting here itself. So thank you all. Thank you very much.
Bye.
I will be closing the meeting here. Hope all have filled the attendance.